Hi everyone. So the topic for my today's talk is learning F# by designing your own language. And the reason I wanted to talk about this is because I know there are a lot of people out there that want to learn F#, but they just don't know where to start. And of course, it's always more fun and more enjoyable to learn a new programming language while I get to build something with it along the way. There are actually many different things you can build with F# to learn it. The reason I went with language parsing as a starting exercise is because I feel like it's one of those areas that really helps showcase the different functional approaches and concepts in action, and it's also one of those areas where F# in particular really excels at. So during today's talk, we will be discussing F#. I will give just a brief introduction into it for those who are still unfamiliar with it, and then we'll just dive into a coding session where together we will build a fully functional, simple query language that would allow our users to filter or order data that we may have in our application. Of course, we'll do that entirely in F# and probably learn a lot of things along the way. So let's get started. So first of all, let me introduce myself. My name is Oleksii. I'm primarily an open source developer. In my free time, I also speak at different conferences such as this one, and I also have a blog on my website where I typically write about lesser known or even obscure technical topics that I think more people should know about. My primary stack is .NET, so C#, F#, and I also use JavaScript on the front end. The technologies I usually work with are related to cloud and web, and I also do automation and DevOps. If by the end of the talk you'll find that you have some questions and maybe you won't have time to ask them during the QA session, you can always message me on Twitter. My nickname is at the bottom right, and I'll always be happy to answer any of the questions that you may have. Okay. So what is F#? Of course, we all know that F# is a functional language, but more specifically, it's a functional first language for the .NET platform. And what does it actually mean? Well, saying that a language is functional in the current day and age doesn't really convey any meaning anymore, because most modern mainstream languages are functional in part anyway. What functional first means, on the other hand, is that the language, the syntax, the framework, and everything else surrounding it really emphasize the functional way of building programs and make it a lot easier to do so. Besides that, F# is also a general purpose language, and it's also multi-paradigm, which means that there is no limit to what you can build with F# or how you can do it. Similarly to C#, F# is also strongly typed, but it comes with a much more powerful type system that enables ubiquitous type inference. And what that means is that usually, most of the time, when writing F# programs, you don't even have to specify the types in your code because the compiler is able to infer them automatically. Of course, F# is also open source, just like most developer tools these days, and you can check it out on fsharp.org, which is the website for the F# Foundation, and it's generally just a good place to start. One of the more common questions that I get from people that are just getting into F# is what can this language actually be used for? And one of the more common answers to that, given by various sources, is that it's best to use F# to contain the business logic within your application, and then use something else like C# to handle the infrastructural concerns. And while this approach does make sense and it's valid, it's probably not been given in good faith, because in reality F# can be used for anything, which means that you can actually use it from start to finish to build entire applications in context of, for example, web development or desktop development or mobile development. And you can also use it for data access or data science, exploratory programming, and all the other things you can imagine. Of course, being a .NET language, you gain access to all the frameworks built for .NET, and while you can also, for example, use ASP.NET Core directly, there are a lot of frameworks that make it a lot more easy and more fluent, I guess, to use from F#. But of course, it's all nice, but in reality, when you start to get into functional programming, I guess F# in particular, is that when you go online, search for guides, you get instantly bombarded with all of this different terminology, different words that don't really convey much meaning, and in reality just make it a very disheartening experience because everything just seems so unfamiliar. And a lot of people get into the situation where they just stumble upon that and ask themselves, what do I do to anchor myself somewhere and continue to expand my knowledge, because it can be very difficult. And in big part, that's because there is this paradigm shift that occurs when you go from an OOP first language, for example C#, to an FP first language like F#. And that's because in object-oriented programming, for example, we have the concept of an object that we use to encapsulate relevant data and behavior together. We then have things like constructs through interfaces and classes, and we achieve reusability through object composition. This approach is also primarily imperative and favors mutability in state, because when the data changes over time, we have to overwrite inside the object that encapsulates it, which leads to mutations. Functional programming, on the other hand, chooses a different approach. Here, the data and behavior are completely separate, while the data is usually represented using immutable models, such as records in fsharp. The behavior is typically functions that transform it from one shape to another. We also have constructs through function signatures, and we achieve reusability through functional composition. This approach is also primarily declarative, and instead of mutations in state, it favors immutability and purity. And purity in particular is actually pretty important to functional programming, because many functional concepts, such as functional composition and functional architecture in general, hinges on this idea of purity. And what it means is that, while avoiding state entirely is practically impossible, we want to keep it as far away from our functions as we can. So a function can be called pure if all it does is that it takes some data on the input as parameters, and then evaluates them somehow, and then just returns some data on the output. And it might seem like any function should be able to fit into these constraints. In reality, a lot of the functions that we write may get some data from sources other than the input parameters, such as the file system or maybe some global state, and likewise they may also mutate it. As an example, let's consider these two functions. Both of them try to determine whether a particular date is a weekend, but they do it differently. The first function gets the date from the global state by evaluating the now function, while the second one gets it as an input parameter. Because of that, the first function is impure, since its result is not deterministic. We can't know or influence which date is returned by the function now. The second function, unlike the first one, is pure because the result is only dependent on the input parameters. As such, this function is deterministic, which makes it composable and allows us to easily test it without mocks. So the idea is that we model our domain by separating the data and behavior from each other, and then use pure functions to represent that behavior. We can then compose those pure functions to express the flow of data in our programs, which usually takes form of a pipeline. Although we can't completely eliminate side effects from our code, we still try to push them as far out as we can towards the system boundaries. In the example of isWeekend function, we'll still probably use the now function to get the current date, but we'll pass it as an input parameter instead of relying on it inside the function itself. And the cool thing about it, of course related to our topic, is that parsers are also functional. So a parser can be thought of as a pure function that takes some text as an input parameter and then transforms it into a higher level structure, usually represented by a syntax tree. And since parsers are pure functions, we can also compose them as we would with pure functions. So for example, if we had a parser A that looks for a character A in the character stream and then transforms it into a token A, then we also had a parser B that did the same thing for character B, we could compose it using, for example, the sequential combinator and turn it into a higher order parser that would look for character A followed by character B, then return token A and token B together. Using this approach, we can build more complex parsers from simpler ones by composing them as functions. Of course, in fsharp this is already a solved problem thanks to a library called FParsec. This library can be used to write recursive descent parsers, which means parsers that can handle languages with recursive grammar as opposed to just regular grammar, and it provides a nice functional API to do so. Just like explained earlier, we can use it to express grammar rules in our languages using parsers, which are themselves functions that take a character stream as an input and produce some higher level types as the output. In order to express more complex grammar rules, we would first start with the primitive parsers, such as a basic string or a character, and then compose them into more intricate parsers using various provided combinators. By doing that, we typically get a hierarchy of parsers that resembles the target syntax tree that we want to parse. Besides that, FParsec is very well optimized for performance, to the point where parsers written with this framework can compete in speed against even hand-rolled manual parsers, which typically take a lot more effort to write. So let's quickly jump into JetBrains Writer, so I can show you the basics of fsharp so that we'll understand what's going on, and also the basics of FParsec so that we can continue with the presentation. So here we are in Rider, and I just created a new project. So this is the code you get automatically when you use the .NET New Console template with language set to fsharp. As you can see, it just created an entry point function for me, so called main, and it also gets the command line arguments as the parameter. And then it just prints hello world from F# to the console and returns 0 as the exit code. So interestingly enough, in F# you don't have to specify return a statement because in F# almost everything is an expression, which means in this case the last expression in the function is what the function actually returns. So in this case the main function returns 0, which is the exit code. And F# is a language which is supposed to be simple in most ways, and in this case we can actually simplify this code by removing this stuff. So we don't actually have to write the entry point function because the compiler can generate it for us. So instead of that, we can just write our code as if it were a script, for example. And as you can see, the result still looks right. So it says hello world from F# and writes that to the console. Okay, so let's look at some of the basics of F#. Let's start with how you declare a variable, for example. So in F# you use the let keyword to declare variables and functions. So let's just say let a equals 5. And this looks very similar to how you would do that in C#, where you would just say var a equals 5. But here it has a slightly different meaning, because in F# when you use the let keyword, you actually specify values as opposed to variables. And what that means is that in F# things are immutable by default, whether there are values or records or stuff like that, while in C# it's the opposite. So for example, in F#, if I wanted to change this value to something else, I would probably want to write it like this. But in F#, the equals operator is actually an equality comparison. So in this case, it would say that the return value of this expression is bool, but it's ignored. If I actually wanted to set the value to something, I would use the arrow operator, which, as you can see here, causes an error because a is not mutable. If I wanted it to make it mutable, I would have to actually write mutable, and then it would work. So the idea behind it is that F# makes it a lot easier to write immutable code and a little bit more hard to write mutable code. So let's just keep that for now. And also, the other thing you can notice is that writer automatically shows that the type of this value is integer, which makes sense because we just set it to the value of 5. But it's also how the type inference works in F#. So for example, we can actually specify the types explicitly here, and then it would also be the same result. But then if we change the implementation or guess the value of this assignment to something else, for example, a string, then it would throw an error because that is not an integer. If we didn't specify a type explicitly, it would just infer that we intended it to be a string. So besides values, you can use the let keyword to also specify functions. So for example, if you wanted to make a sum function, we would write let sum and then equals, for example, 3 plus 5. But by doing that, we don't actually specify a function, we specify another value. As you can see here, the data type of this value is still int, and we actually want it to be a function. So in order to do that, we actually have to specify the parameters, because every function in F# has to have parameters. And in this case, let's assume we don't really have any parameters, so that means we have to specify the unit. So by doing this, which is just empty parentheses, we specify that the function sum here actually takes one parameter, which is of type unit. And unit in F# is a special value, which basically denotes nothing. So it's kind of similar to void, I guess, in some aspects. Also, you can see here that the signature of the function changed. So it was int before, now it's unit arrow int. And what that means is that it's actually a function now that takes some unit as a parameter and then returns int as a result. So if we wanted to call it, for example, we would write let result and then call that. And if we just write sum without the parentheses, we would just basically reassign the function to another name. So this is still the same function, as you can see by the signature. If we want to call a function, we have to pass the parameters. And here the parameters are just a unit, so basically nothing. So by doing that, we get an int as a result. And this looks strangely familiar because this is pretty much the same as it would look in C#, for example, where it will look like something like this. But in F#, the semantics behind it are a little bit different because, like I said, every function has to have parameters, and when it doesn't, we just specify parameter, which is a unit. So in this case, if you wanted, for example, to have actual parameters, we would say sum x and y, and then use those parameters here. And then by doing that, we actually have a function that has real parameters, in this case 2 of them. As you can see, we use spaces to separate them. The type signature changed from unit int to unit unit unit, mostly because now the compiler is not able to infer the actual types of the parameters, since we're calling the sum here with the unit as a parameter, which is not correct. So let's just change it to sum 3 and 5, and that makes things right again. So now the signature of the function is actually int to int to int. And what that means is that it's a function that takes int as a parameter. When evaluated, it returns another function that also takes int as a parameter, and that when evaluated finally returns an int value. So this is what a curried function is, essentially. Basically, it's a function that you can apply partially. So every argument is essentially you apply it one by one and you get a function as a result. So in this case, we could have, for example, only applied one of the parameters, and then we would just get another function as a result, which has one less parameter. If we wanted to have the parameters passed at the same time, we could use the tuple. So if we wanted to do that here, we would write it like this instead. And the implementation would remain the same, but the way we call it would again look similarly to how it looks in C#. So here we would just write it like this. So in C# we would call it like that, but again in F# the semantics behind this are a little bit different. So here we are actually passing a tuple of values as a first and only parameter to this function. As you can see, the signature has also changed, so it was int to int to int. Now it's int multiplication sign int that returns an int. So a multiplication sign in data types in F# actually means that it's a tuple. So in this case, it's a tuple of 2 values. We could, of course, extend it to 3 by doing something like this. That would cause an error here because we only specify 2 values. So let's say 8 here. That would work on 3 values, as you can see. And we could actually also have multiple tuples as parameters. So we could have t and u here as well, and then also have them used as the inside the implementation. And that would just mean that this is now again a curried function, but it takes tuples as parameters. So we could also apply some values here, and that would yield us the result. Of course, it's a little bit of a convoluted example. We don't actually have to write something like this most of the time, but this is basically how things work in F# as far as functions and values go. Okay, so now let's take a look a bit into FParsec. So I already added this as a reference here. So as you can see, it's a package reference. I just used NuGet like you would with any .NET language, so this thing is pretty simple. And in order to use it, it provides a lot of functions that are top level. So in order to use it, we have to open the main module, or the namespace, I guess. So the module, or sorry, the open keyword, or I guess the declaration, I'm not sure how it's called, works pretty much the same as the using the declaration in C#, so it's pretty much the same thing. So okay, let's clear this thing up, remove all the things that we've wrote. And in FParsec, there are a lot of functions that it provides straight out of the box. So normally you would look at the reference guide that shows what they are and what they're used for, but we're not going to do that, obviously. I'm just going to walk you through them. And in FParsec, all of the functions that it provides can be logically separated into 2 groups. So the first group is the primitives, which are the functions that generate parsers for very primitive things. For example, just parse a string or parse a character, or maybe parse like a group of characters that have the same trait. And the other group is the combinators. So those are different functions, and those functions actually take other parsers as parameters, and they wrap them into something more complex that does something more complex, basically. So let's take a look at some examples. Let's say we want to create a parser. So the way we do that is that we specify a value or a function in this case. Let's just call it p for now, and let's just use the pstring function that creates a parser that just looks for a specific string. As you can see, the description is pretty self-explanatory. So it says that pstring str parses the string str and returns str. So it's a pretty primitive parser, and let's just pass hello to it. So by doing that, we actually got a parser here. As you can see by the type signature, it's a parser of string and object. And in FParsec, we can actually handle context-sensitive grammar, which has state. So the second generic argument actually denotes the type of that state. We don't actually want to use it here, so we can just ignore it for now. So in order to run a parser, it's just basically a function. We can pass it a character stream, but to make things a lot easier, FParsec actually provides a function that allows you to pass more concrete values as parameters to your parsers. So this function is called run. So for example, let's say let result equals run. And there are different types, or I guess variants of this function, but we want to use the basic one, which takes a string as a parameter and just returns the parser result. So this is pretty simple. Let's just run it on the exact string that it expects when we forget the parser. So let run p on hello. And then in printfn, let's just change it so that it prints the result. And we have to specify the format. Let's just use the generic object format. And let's run our program to see what it prints. So by doing that, it prints success hello, because we are basically creating a parser that looks for a string hello and returns it. And then we run it on the exact string that it expects to find. So this is pretty trivial. And let's see what happens if we actually change the string to something else. So for example, from hello to goodbye. Because now the parser that expects to find hello will not be able to do so. So the result of this operation will be a failure. But on top of that, as you can see, FParsec actually generates a very nice error message that says where exactly the expectations were not matched. So in this case, it says the error is on line 1, column 1. So it found goodbye, but was expecting hello. So that's pretty nice, because with FParsec, we actually have automatic error messages, which are actually customizable, so you can change how the expectations will look, and so on and so forth. We'll not get into this today, but it's nice to know that it's there. Okay, so this was just a primitive parser. Of course, in real world, we don't get much by parsing a string and turning it into a string itself. Let's just complicate things a little bit. So let's change that to parser A. And let's also have another parser, let's call that B, that also parses a string, that parses a specific string world. And one of the things we can do in FParsec is that we can combine those parsers in different ways. So let's just create a parser P that combines them using the OR operator. So in this case, the OR operator, as you can see here, is one of the operators defined by FParsec. So F# actually allows you to define many custom operators. And what this one does is that it takes a parser on the left, takes a parser on the right, and then combines them together in a parser that will succeed as long as either one of those succeeds. So basically, if we pass hello, it will succeed, or if we pass world, it will also succeed. We can check that. So let's type hello in this case, and we should see the same result as we did in the beginning. So it just returns hello. But if it, for example, type goodbye, then it will obviously fail. But the error message now contains the different expectations, where it says it wanted to find hello or world. So FParsec actually, when you combine parsers, it also combines the expectations, so their messages look very nice. And like I said earlier, it's not really much use to parse a string into a string, because the whole idea of parsing is that you take a low-level construct, which is text, and turn it into something more concrete, such as domain types. We actually probably want to parse, convert the result of those parsers into something else. So let's just define a type. For simplicity, let's just make it an enum. So the way you define types is that you use the type keyword, and then just give it a name. So I'll just give it a name token. And then since it's an enum, we just want to enumerate the values that it can actually represent. So let's say token hello, or sorry, you don't have to actually specify tokens, so just hello, and then the world. So let's say that you have an enum that has two cases. And in case with the first parser, which parses hello, we don't want it to actually return a string, we want it to return this token. So the way we can do that is we can use this operator. And then we just type the object that we want to return. So in this case, token hello. So what it does is actually, if we hover over the pointer, it actually shows the description and the signature. So in this case, it just takes a parser on the left, and then any type, instance of any type on the right, and then just converts that parser, ignoring whatever result it may have, to a parser that just returns this value. So basically, we are looking for a string hello, and then if we find it, we turn it into a token hello, so a little bit higher level construct. As you can see now, the parser that combines the A, B, and parser together shows an error because the return type of one of the parsers is string, while the other one is token. So we actually have to have those parsers aligned by types in order for them to be combined. So here we will also do the same thing. We'll say token world, and that turns this parser into a parser that returns token world in case it's successful. So if we run it on world, for example, and see what happens, the results should also be successful, obviously, but the difference now is that it returns an actual enum value. So as you can see, it says success world, but unlike the previous examples, it didn't encapsulate it in quotes, which means it's an actual object. As you can see, it's also uppercase, while the actual string wasn't. And this is actually the whole idea of parsing, in which we take some value from a string and turn it into something more concrete or higher level that we can actually represent using domain types, and then analyze or convert to something else later. So that concludes the basic intro to F# and FParsec. And then let's go back to the presentation once more and continue and see how we can actually use all of this knowledge to build our own query language. So now that we know the basics of FParsec, we can actually move on to building our own query language. When designing a language, the first thing we have to do is come up with a good language syntax. As you can see, I've already done this part beforehand and wrote a small example of what an input in our query language would look like. Here we can imagine that the user is provided with a list of books and they want to filter them by a specific category, order them by their online rating, and then take a small portion of the results. So when you're designing the syntax, what you're actually doing is that you're trying to represent your language in a more formal way. When we reason about code as humans, we don't really have to consciously think about what each part of the input stands for, but in order to teach the computer to understand our language, we have to formalize it. In case with this syntax, we have a number of different language constructs, for example keywords, which are a reserved sequence of characters indicating the type of a statement, for example filter by, order by, skip or take, or the order of the direction that we want to use. Besides that, we also have identifiers, which reference a specific property on the objects we're dealing with. Using identifiers, we can filter and order items by the actual values of their properties. Then, of course, we also have literals, which are essentially just constants. In our language, we will have integer literals, just like the ones used in skip or take, string literals, just like the one in filter, or float literals, which are not really shown here. The parts in between keywords, which are composed from identifiers, literals, and other things, are called expressions. Expression is a basic construct in almost any language, which simply denotes some operation that can be evaluated to some result. So in this case, we can have, for example, the string literal fantasy, which simply evaluates to fantasy, the category identifier that evaluates to whatever is the category on a particular book, and the comparison operation which evaluates to true or false, depending on whether those two match. Finally, we have statements, which are individual instructions separated by new lines. A statement is denoted by a keyword and contains an expression. So at the end of the day, the result we're looking for by parsing this input should look something like this. So this is the syntax tree of our language. As you can see, for the most part, all of the statements in our language look pretty similar. They are all composed of expressions, except for order that also takes a direction as a parameter as well. So let's take a look at expressions in more detail. Just like mentioned earlier, the expressions in our language can be represented by, for example, the integer literal, which is represented by an int data type, a floating point literal, which is represented by a float, a string literal, which is represented by a string, an identifier, which is also represented by a string, but evaluates to something more concrete, and also a binary expression, which is a lot more complex. Things like the equality comparison that we saw on the previous slide in the filter statement, or the AND or OR operator, or the plus or minus, all those things are binary expressions. And the reason they are called binary is because they take two expressions as parameters. So what it essentially means is that the expression may also contain an expression itself. So in case with binary expressions, we may have an expression inside of an expression inside of that expression, and so on and so forth. And that makes this grammar rule recursive. The fact that our language is recursive means that our parser should also be recursive in order to handle it. That also means that we can't just use things like regular expressions in order to parse it. Cool. So now let's jump back to JetBrains Writer, where we will express all of the language constructs we've just seen using fsharp data types, and then also write parsers for them. So here we are in Writer once again, continuing where we left off. We can actually remove all the code that we've written so far. And let's just create a new file where we will define the types related to the language constructs in our query. So let's just create a type called query. And by doing that, as you can see, Writer suggests the different options that we have. So we can have a module file or a namespace file. The difference between the two is that in the module file, we'll just have one module. In the namespace file, we can have multiple. So let's just go with the first option, a module file. Let's call it query. Let's zoom it in a little bit. And what module actually is in F# is that it's basically a way to group related things together. So in a module query, we will just define the types related to our query, also the functions that we may have, and all the parsers that we will use to parse into those instances of those types. So let's start with the type definitions, and let's define the expression type because it's the one that's used in basically every statement. So in order to define the type in F#, you always start with the type keyword. So in this case, type, and we will call it expression, so XPR for short. And here we actually have multiple cases for an expression. So as we remember from the slide that we've seen in the presentation, we'll have an int literal, a float literal, a string literal, identifier, and a binary expression. And this is kind of like an enum, but besides being an enumeration of different values, each of those cases may also have some data that it encapsulates, right? So for int literal, we will have some int value, and for a float literal, it will be a float value. For a binary expression, it will be an expression and then another expression. So in order to define that, we actually need to have a discriminated union. And the way we define discriminated unions is actually very simple. So we type equals, and then let's define our first case, which is int literal. And just by doing what I did here, it becomes an enum. But in order for it to be a discriminated union, we'll have to specify the data type of the value inside of it. So in this case, it will be of int. So by doing that, we've defined and int literal union case for the expression type, and that union case has the type of int. We'll do the same for the floating point literal, so float literal of float. And here it's an interesting point because a float in F# is not actually a system float, it's system double. So this is something to be aware of. Then we also have the string literal and the identifier, which also has the string data type. The most complex one is, of course, the binary expression. So binary expression will have two expressions as the parameters, I guess, and also the kind, which will specify the type of the expression, because we will have, for example, the equality comparison, the greater than, lesser than, the and or operator, plus or minus, and so on and so forth. So in order to do that, we have to define a tuple, because we'll have multiple values, and that will be a tuple of expression, expression, and binary expression kind, which we'll have to define now. So let's just do that. So let's define the binary expression kind. And the way everything works in F# in relation to, I guess, references is that you can only reference types that have been specified or defined earlier than wherever you want to reference it. So in this case, for example, in line 10, I want to use binary expression kind. It would only work if it was specified before the expression type. And that actually helps you because it protects you from accidental recursions in your type definitions. So you won't have cyclomatic references that you don't really need. But if you also want to do that, you can do that, but you have to do that explicitly. In this case, we don't really need that, so let's just proceed to defining the binary expression kind type. In this case, it will just be an enum, so you don't have to have any additional data. And here we'll just define all the different operators that we may have in our language. So let's start with the basic ones. So for example, the mathematical operators, add, so the plus operator, subtract, the minus, then also the multiply and divide. That should be enough related to mathematics. Let's also add some logical operators, so and or, which will work with Boolean values, and also some just generic comparison operators, so equals, not equals, greater than or equals, and then also, of course, lesser than, and lesser than or equals. That actually should be enough. Of course, we can add more types or expression kinds later, but that seems to be enough for our users to build different filters and order statements. So let's just keep it this way. And if you're curious how the discriminated unions are actually instantiated, so let me show you how that works. So if you wanted, for example, to instantiate an int literal, we would write let a equals. Then we just use the case that we want. And in this case, the int literal union case, as you can see, if I hovered my pointer over it, it says that it's a union case. But then after the name, it also specifies the type as int error expression, which means it's a function. So every union case, wherever you specify it like this, is actually also a function that constructs it. So in this case, as you can see, it takes an int. So in order to initialize it, we have to pass some value. And that turns the value of a into an expression. The same way it would work for other things. So if you wanted for it to be a string literal, we would have to use a string, but also, of course, have the union case be a string literal. And with binary expressions, since we can have nested expressions, it's a little bit more complex. So with expression binary, we would have a tuple. Here, let's say that's expression float literal, like 314, then expression int literal, 15, and then maybe binary expression kinds greater than. So that would be how a very simple binary expression could look like. Of course, we could also nest binary expressions inside of it, so there could be expression binary with expression binary on the left, and maybe expression binary on the right, and so on and so forth. And this is exactly what our parsers will have to do. So they will have to read some text and then turn it into this, essentially a hierarchy of expressions. So let's actually finish defining the types. So we still have a few more. So the next one is obviously the statements. So a statement would actually have 4 cases because we have the filter by, the order by, and skip and take. And in the case with the filter by, again, it's a discriminated union of expression, right? Because we can filter by an expression. In case with order, it's a little bit more complex, so it's an expression, and it also has a direction. So let's tentatively use it here, but then we'll have to define it here as well. So in order direction, it will be just an enum that can be ascending or descending. All right, and then we also have skip. A skip will also be of type expression. And actually we can simplify it and use int here because it's probably unlikely that anybody would want to skip by some expression. It's always going to be a number. So just for simplicity, let's use an integer here to make our job a little bit easier. And also the take is the same. Finally, the way our language works is that the syntax tree is actually a list of statements, so we can have multiple statements, maybe multiple filters, maybe just different statements, and we have to find a way to group them. So let's just create another type called query, and here I just decided to use a record instead of a discriminated union. So here I'll just define a record that has a property called statements, and that has a type of statement list. Okay. So a record in F# is kind of similar to a class where it just has properties that you can define, and that class or record is essentially immutable, so you cannot change any of these properties after you created an instance of this type. If you want to change them, of course you can, but you'll have to create a new instance as well. And here we also define the type for statements as a statement list. In F# you can use the postfix notation for many generic types. So this is the same as a list of statement. Okay, great. So I think that's all as far as types go. Let's actually define the first parsers or implement the first parsers. So before we do that, of course, we have to open FParsec because we'll use the functions from that namespace. And let's define our first parser. The easiest thing I think that we can do here is parse the string literal. So let's start with that. A string literal in our language, as we remember, is just a string enclosing quotes. So it would look something like this. And in order to parse it, we'll have to look for a single quote, then just discard it, and then just parse any sequence of characters that comes after it until the next single quote. So in order to do that, we actually have to combine multiple parsers together. So let's create a first parser called quote, and this one is pretty simple. We'll just say pchar and then quote. In order to do that, we'll have to escape it. But since we're not going to actually use the quote, we'll just be skipping it. We can actually use the skipchar variation, which does the same thing, but it doesn't return a result. And here it highlights that there is a value restriction error here because, as you remember, a parser has 2 generic arguments. So there is the return value, and there is also the type of the context. Since we're not using the context anywhere, it can't really infer it here. But this error will go away eventually, or we can just specify the type ourselves like this. So we just explicitly said that quote is a parser of whatever, so still infer the result, but use the unit for the context type. Okay, so a string literal in our case will be a quote, but then it will have to be followed by something else, right? And the way you combine parsers sequentially in F# is that you use one of the sequential combinators. More specifically, we have to use this one. There are also other ones, such as this one, for example, or this one. As you can see, they differ based on where the pointer or the dot is located, and the dot actually points towards the result we want to keep. So in this case, we'll keep the result on the left. In this case, we'll keep the result on the right. And in this case, we'll keep both results combined in a tuple. So we don't actually care about the quotes, so we'll just use this one. And we want to combine it with another parser that will look for the parse the string inside the quotes until the next quote. And to do that, there is a pretty good primitive called miniature still. As you can see, there are a lot of different variants. We just need this one. And from the description, it says that this function takes a parser for the characters, so the characters inside the enclosure, and then the end parser for the parser that will check whether the sequence has ended. So in our case, the character parser will just be any character, and the end parser will be another quote. So we'll just use that, pass the any char as the first parameter, so any character will do, and I'll just use quote as the end parser. So there you go. We can actually test how it works. So in order to do that, we can open FParsec in our program and run this parser. However, the problem is that when we created a new query, or sorry, a new file called query, writer automatically put it below the program. As you can see, it's actually also reflected in the project file. And fsharp is pretty special in the sense that in fsharp, it matters how the files are ordered. So similar to how inside of a particular file you can only reference types or functions that were defined earlier, you can only reference, for example, query from files that were have the order below it, right? So in this case, we can't actually reference query from the program because it's above it. We can change that by just dragging the query file above it, and that reflects in the project file as well. So now we can go to our program. We can just also open our own modules or query, and then just run the parser. So let result run string literal, which is the parser that we just made, and run it on an actual string literal. So in this case, let's say hello world, and just print it to the console. Right, so let's see how it works. Let's use the terminal once more. And it's successful. And as you can see, it also returns the hello world string like we are already used to it by now. So that's pretty good. But obviously, we don't really want this string. We actually want the literal case of the expression, which we didn't really use here. So the parser actually returns the string, but we can change that. And in order to do that, we can use another operator, which looks like this. So previously we've seen this operator, which just discards the result of the previous parser and just returns something else entirely. This parser is different because it uses a mapping function to turn an existing result into something else. So in this case, we actually need the string that we've parsed here because we want to encapsulate it into a string literal. So here we'll write the expression string literal. And as you remember, a union case is already a constructor function, so we can just pass it as a function inside of the separator, and that will just work. And now it returns a parser of an expression. If we run our program once more, that will now return also a successful result, but that will be a string literal of hello world. So that works pretty great. Now let's continue and actually write the parser for the int literal and the float literal. And we can actually do those two things together because FParsec provides a very nice primitive called number literal. So let's define a new parser called, let's call it also number literal. Actually, we probably can't, let's call it int or float literal. So it's a little bit more expressive. Then we want to set it to a number literal, which is the function provided by FParsec. As you can see, it takes two values or two parameters, which is options and label. And then it parses the number according to the options and the label is used for error formatting. So we can say number literal. The options we're going to use are number literal options, default float, or default integer. So in F# you actually use the triple pipe operator to combine enums, because the single pipe operator is reserved for something else. So other than that, it's exactly the same. And for the label, we'll just say number. So the label, like I said, is just used for string, for formatting the expectations to a string when there's an error. And now that we have the number literal, we actually want to turn it into our own expression here. So let's make use of this operator that we've seen earlier. And in this case, we have more complex logic here. So we'll define a lambda function. So fun n arrow. And here we want to see what actually has been parsed. So let's check if n is integer. And in case it's an integer, let's just return an expression of int literal. Here we just need to parse the actual value and pass it to the constructor function. So here we can do int, which is the built-in function to turn a string into an integer, and pass the actual string that it has found in the input. And of course, as you can see, if I hover, it says that the if expression is missing an else branch. That's because in F# everything, like every if expression should have the corresponding else expression or else branch, because you can't just have it hanging, like only handle one of the cases, not the other. So let's also define the else one. And here we'll use the expression float literal and return a float and string. Okay. Let's also just define an expression parser, which will be either an int or float literal or a string literal. It also gets rid of the error, so because the types of the parsers have to match, and we also have already one of the parser defined as having a unit context, so that the error is now gone here. That's great. And we can actually test it in our program, so let's change the invocation here to use the expression parser. And then let's say 314, for example. So let's run that. And when we do that, we just get a successful result as expected, and that contains the float literal expression that has 314 inside of it. We can similarly just do, let's say, 14, and that would return the int literal with just 14 inside of it. So everything works great. And then we also have the identifier expression. And let's just say that for identifier, we'll just parse a string without any quotes or anything like that, made out of letters or digits, just for simplicity. So let's just assume we can have only letters and digits in property names. So let's say let identifier equals, and then here we just want to parse many characters. Let's just use many chars function, but we'll use this variant because, as you can see, many one chars parses the sequence of one or more characters, while the many chars variant only parses or can parse 0 or more characters. In this case, we actually want to only succeed if at least one character has been found, so let's just use this one. And for the character parser, like I said, let's just use letter or digit. FParsec already provides those primitives for us, so let's just use that and combine that with digit. And we could also merge it together into the expression parser that we have, so doing it like this. But it is actually a little bit more, I guess, performant to use the choice combinator instead, because the choice merges parser or combines them together as a list, as opposed to doing that pairwise. So we can just do the same here and say int or float literal, string literal, and then identifier. Identifier is highlighted in red because I forgot to turn it into an expression. So the type system actually helped me and let's say that is expression identifier. So cool. Now we can also, let's say category would be one of our properties. So let's see how it parses that. So it's successful and it just returns identifier category. So that works very well. Now we have to proceed and make a parser for the binary expression. And this one is a little bit more tricky because a binary expression can be recursive. And on top of that, we also have problems like associativity and precedence. Because, for example, when you have operators such as plus and multiply, the multiply operator always comes first, even though it might not be the first in the order it's typed in. So we could actually handle that ourselves, but luckily FParsec already provides a way to do that for us. And let me just go back to the presentation one more time to talk a little bit about it. Parsing expressions can be pretty tricky. First of all, that's because they're recursive, which means that an expression can contain other expressions and so on and so forth, but also because with the different operators, you have to handle associativity and precedence rules. Luckily, this is such a common problem that FParsec has it already solved for us. It comes with a type called operator precedence parser, which you can configure with your own operators, and it will parse the recursive expressions automatically and also handle associativity and precedence rules itself. So let's jump back again and see how we can use it. So here we are back to code once again. This time I wrote some of it beforehand because I realized that I'm running a little bit low on time. So what I did here is that I created a new instance of the operator precedence parser class configured for our expressions. So the term parser property of this instance is actually what we had previously as the expression. So the term is the thing that goes between the operators. In our language, in our case, that's our literals and also the identifiers. So I set the term parser to that parser, and also I added all of the operators in our language. And all of them are also infix operator, which means that the operator is in the middle between the operands. And for example, here I configured the multiplication operator by specifying what it looks like. Then the next parameter specified the after string parser. So we could actually have another parser for the string that goes after the operation. What I used here is the whitespace parser, which just discards any number of whitespace characters afterwards. So that means that the user can use whitespace basically as they want, and we just will ignore it as long as it's not new lines. Then I have the precedence configured here. So the multiplication operator has a precedence of 1, which means that it will go and take precedence over, for example, the plus operator, which has 4. And also I used associativity left for it, which means that if there are multiple multiplication operators, they will be grouped towards the left side. Okay, so 3 times 5 times, let's say 7, we'll first group them towards the 3 times 5, then the result of that will be calculated for the times 7. Then finally I have this function that converts the terms to the binary expressions, so x and y are both expressions, and then I just create a binary expression out of it. The same pretty much applies to all of the other operators. And now that we have that configured, we can actually redefine our expression parser to use the expression parser provided by this instance. So if we test it out, let's say here we actually want to check if the category equals fantasy. This is something our users would want to do. So let's see how that works. And that successfully returns a binary expression, which on the left side has an identifier category, and on the right side has a string literal fantasy, which is of type equals. So that works exactly as it's supposed to. Cool. So let's also define the parsers for the remaining parts of our language, which are the statements. So we just need 4 more parsers for those. So let's start with the filter statement. First of all, of course, we have to make sure that we start with the keyword filter by, as dictated by our language, but then we also have to have a space between it. So in the language that we have, the keywords are separated from the rest of the expression using at least one whitespace character. So we have to actually have to implement another parser, which is, let's call it one, which will use skip meaning one skip character space. So that means that it will skip all the whitespace characters, but it will make sure that at least one was found. So we'll use that one instead. And then after the whitespace, we don't really need to retain that result, so we just skip that. And after whitespace, we're looking for the expression, so let's just use the expression parser. And then afterwards, we also might have some whitespace as well, but in this case, we don't really care about it, like what is the actual number of the whitespace there. And finally, we want to map that to filter by statement. So the others are the same. Let's say order by skip string order by. In this case, it's pretty much the same. So we start with an expression, but as you remember, besides the expression, we also have the order direction. So let's also add a parser for order direction. And let's start with adding one for ascending case. So in our case, let's say skip string ascending, and that will return just the order direction ascending. And I'll also skip the whitespace afterwards. And also we have order direction descending, which will do the same, but for the other case. Okay, so that's also skip whitespace there, and then we can just combine them to a single parser of higher order, which is order direction. So that one will be either this one or that one. So here, after expression, we'll return that result, but we also want to have the order direction as well. So we'll use this operator instead, and use the order direction parser that we just created. And then finally, we ignore any whitespace that comes after it and map that to statement order by. For skip and take, we decided to go with a slightly simpler route. So we'll just use the integer parser. So in this case, we'll just start it the same way. But instead of an expression, we'll just use pin32, which just parses a normal integer, and it's already built in and provided by FParsec. So that just maps to statements skip. And the same for take. So take. Finally, we can have a parser that combines those two, or those four statements. So let's just make a choice combinator there, and let's say filter by, order by, skip, or take. So it can be either one of those four. And then, of course, as we remember that our statements are combined into a query, so we need a list of them. So we can create another parser which is called query. And what it will do is that it will use the combinator call separator and by, which will look for the parser separated by another parser. So we'll use that, and our main parser is statement, and the separator is skip new line. So our statements are actually separated by new lines. And that returns the statement list. So we want to map that again to a query, which is a record. And in order to do that, we just have to initialize a record by using the curly braces. So here we're just going to say statements equals, and then actually need a function here. So function, let's say s equals s. So now the parser actually returns query. So it automatically inferred that an object that looks like this is our query record. So that happens automatically. And then finally, the last thing we have to do is create a parser that wraps around the query and also makes sure that it is the only thing that exists in the input. Because currently, if we run the parser on some input that might have occurred and then something else, it will just parse the query and stop there. But what we want to do is to make sure that there is nothing coming afterwards, because that would probably signify an error. So let's just create another parser called query full. And here I'm just going to wrap it in spaces so that we can have spaces in front and in the back. And then take the query and then also have some spaces afterwards. And this spaces function actually also skips not just the regular spaces, but some other ones, including new lines. So that's why I didn't use it before. And finally, we have to make sure that's the end of file. End of file also means end of input in case we are passing a string. Okay, that's pretty good. And just to make it a little bit easier for our users to use our parser, we'll just provide a parse function. And here we're just going to use the run function like we did ourselves. So run query full on the input. But we're going to pattern match it with the result that it can have. So since it's a parser result, it can have a result which is successful or a failure. So let's say success, and then it has the result inside of it, but also some other parameters that we're not particularly interested in right now. And we'll just map it to a more standard result, which is provided by fsharp out of the box, which is also a discriminated union. And in this case, we're just going to return OK. In case of failure, we'll just return the error. So here we just return error, error. That looks good. So now we can go back to our program and actually change it so that we don't have to use FParsec there. And instead just use query parse. Actually, it's already in the top level because we opened it directly. And then parse some input, for example, like we said, filter by category equals fantasy. Okay, so let's see what that does. So by running it, it actually doesn't do anything because it returns an fsharp result. That's fine, so we just need to match it here as well. So let's just do that. Let's change the input to put it into another variable. We'll use the triple quoted string here because that makes it lets us do multi-line strings very easily. So it's the same as a verbatim string in C#, for example. And let's just expand this as well to use something else like rating, descending, skip 5, take 10, for example. And then parse that, so parse the input, and then match it again, the result with our results, which is result OK. In this case, this is what we want to actually print. So we'll do that and say print result. Or in case of error, we just want to print the error for now. So just to make things simpler. In reality, we'll probably also have some other like fallback mechanisms or something like that. So if we run that on our new input, we'll see that the parser succeeded, and it returned a record of statements. And the statements contain the filter statement, which is a binary expression category fantasy and equals, order statement, which is a rating and descending, and then skip 5, take 10. So that parsed the whole input absolutely correctly. So that's great. So now that we have the parser for our query language, we actually also want to have a way to evaluate our queries. So in order to do that, let's also add another function called execute. And then we'll have to pass a query to there and use some list as a source. So let's do something like that. And inside of it, we actually have to have a way to evaluate the expressions, right? Because in many cases, we just have expressions and we need to evaluate it on a particular element. So let's also add another function called evaluate that takes an expression and an element. And that will have to match the expression with a lot of different cases that we have. So obviously we have the int literal. And in the case of the literals, we just return them as is. But since we'll have different types here that might be returned by the expressions for example, int, float, strings, and then for identifiers, it could be anything pretty much, we'll have to cast it to the object type. So we'll just do that. For float literal, it's pretty much the same, so cast that as well. For string literal too, so do that. And it's important in fsharp because in fsharp, it doesn't cast things automatically. And that's also just something it does by design. So in case with identifier, it's a little bit more tricky because we have to get the value of a property from reflection. So we'll just use get property, use the name provided, and then get value, and then element. That already returns an object, so we don't have to cast it. And of course, then we have the binary expression. So when pattern matching it, we already have the values provided. So it has the left, right, and kind. And then we have to match on the expression itself here. So I actually have, so in order to do that, we actually have to match the kinds. So do that, and already have a snippet that I've prepared here so that we can make it a little bit faster. So yeah, there we go. So basically, this is the pattern matching for every operator that we have. So add, subtract, multiply, divide, and or equals, and blah, blah, blah. And here when we match it, we use the evaluated result, which we don't have right now. So let's do that. So let's say left evaluated is the evaluate left on element. So basically we want to call the same function to evaluate the inner expressions. So in essence, that becomes a recursive function. And in order to do that, we have to mark it as such. So in F#, functions have to be marked that they had to be used recursively. So the same for right evaluated. So we have to evaluate the right side, and then we can actually use those values here. As you can see, when adding two operands together, I cast them to floats, and then when I use the logical operators, I cast them to booleans, because I cannot use those operators on anything else. And then for equality and comparison, I actually use the iComparable. Okay, so now we can actually apply all the different statements that we have. So let's start with the filter. Say, actually, I think I'm missing a open system here. That should probably solve it. There we go. So let's add the function that says apply filter. And that will take an expression which is inside of the filter and also the list. So let's say LST. And let's use the built-in function list filter. It works the same as the where in link in C#, but it's just a static function instead. So to use it, we have to pass the predicate and also the list we want to filter by. So in this case, the predicate will be our evaluation of the expression on this particular element. We also want to cast it to bool because we need it to be a boolean value, and also use this list that we provided. Then we have to create a function to apply order, so that one has an expression direction in the list as well. And to do that, we have to match on the direction of the order. So in case with the ascending order, we'll be using list sort by, which also takes a function as a parameter. In this case, we will evaluate the expression on I once more, but this time we'll cast it to iComparable so that they can be compared between each other. And then use the list once again. And then for descending, the same thing applies, except that we will use the sort by descending here. Finally, for apply skip, we'll just use the count and list. So if count is less than list length of our list, then it's all good, and then we'll just apply the skip operation here. So count list, and otherwise let's just return the full list instead. So in F#, unlike link, if you skip too many elements, it will actually throw an exception. So by doing that, we avoid that. And for take, it's pretty much the same thing. So let's just copy paste this and change this to take. Finally, in order to apply all of these things together, we have to do something special, right? Because we have a list of statements coming from the query, from this parameter, and we want to apply them on the list of items that we were given. So in object-oriented or imperative programming languages, we would do that using a while loop. So we would have the current list, and then we'll basically mutate it every time we go through a statement. That's not an idiomatic approach in F#, of course, so we'll use the fold instead. So a fold function just takes a list and then applies a function to each element in the previous state that we currently accumulated. So the first parameter is the folder function. So let's say function and then current and then also statement, because we're going over statements. So match the statement with, and let's say it's a filter by statement, so an expression inside of it. Apply a filter to this list, so current. In case it's an order statement, we'll do the same, but with direction. So apply order expression direction list. So in this case, it's current again. Then skip count, apply skip count current, and then take count, apply take count cur. And I just realized I made a small mistake here, so let's correct that. And then after that is done, we also have to specify the starting state, which is the source, the first initial version of the list, and then also what we're folding, which is the list of statements. So by doing that, if we go back to the query, as you can see, or the function as you can see it, inferred that the query is a query, and then the list is just a generic list, and we also return the list of the same type. Okay, so now we can actually test it on some input. So I actually prepared a basic sample here. So this is the list of books. As you can see, it's also a record, and I just have a few of them here. So let's just preload them in our program. So let's say let books equals books. Actually, let's open queries for us to be able to get that. So get all, that gets us the list of books. And in case the parsing has been successful, let's actually evaluate the query on that list. So here we will instead, I guess the result on, the query result, let's call it that, just to make it very confusing. And then we'll apply use the execute function, use the query, so in our case the res, and then apply it on the books. That will be the query result. And then we can actually iterate over and print it. So let's use the list iterate function, which is basically kind of like a for loop, but it's used as a function here. So for each element, we'll just print it. So let's say print it as an object, and then use the query result, which is the list of books. So for starters, let's just remove the query, see how it works with the full list. Let's do the .NET run command. And that seems to return all of the books. So basically, when the query is not applied, it just returns the original list, which seems fine. And now let's actually use the queries, so filter by category fantasy and order by rating. Probably too many to skip, so let's just not skip and take for now. Let's see how it works. So the end result here should be that the query or the result contains only books from the category fantasy, as you can see, and they're ordered by the rating. We can actually change it to order it in a different direction. So the fellowship of the ring should be the first one now. There we go. And let's say we only want to take one, so let's say take one. So there you go. So we've actually succeeded, and the query parser and the interpreter seems to work correctly. So let's go back to the presentation and conclude this talk. Great, so now that we built our parser, we also built an interpreter that takes the result of that parser and evaluates it on any collection of items that we may give it. Since we have done so many things, we've probably learned a lot of things as well. One of the first things that we've learned is, of course, the F# syntax, how you define values, functions, and types, and also the project structure. The major difference here compared to C# is that the order of files in a project actually matters in F#. Besides that, we also looked into data types that F# provides, as well as how to define your own records, discriminated unions, and tuples. Of course, we also looked into pattern matching, which is used ubiquitously in F#, and functional composition that we've used thoroughly to build our own parsers. On top of that, of course, we learn how to write our own language parsers, which are used in things like compilers, syntax analyzers, transpilers, and so on and so forth. And then we can use those skills acquired to build even more complex programming languages. In case you want to check out the source code to the project that we built during the coding session, you can find it on GitHub. Additionally, the repository will contain the presentation that I'm currently showing. Should you want to learn more about FParsec or maybe F# in general, then check out one of those resources. For example, if you wanted to learn more about F#, then the blog by Scott Flushing called F# for Fun and Profit is a very good place to start. He writes about the different functional concepts and F# related things in a very approachable and simple to understand manner. If you wanted to learn about FParsec, then the official tutorial by the author of the library, Stefan Tolstorff, is also a good place to start. Additionally, I also have a blog post of my own called Parsing and F# with FParsec that you can check out. So I guess that finally concludes the end of my talk. So thank you everybody for your attention. I hope that somebody found this interesting, maybe learned a thing or two. I'm very grateful to be able to speak in front of your screens today, and thank you and goodbye.